Students, we will see the next topic in this unit, unit number 5. So here we have seen the radiation sensors and LDR. Now we shall see the next important topic, fiber optic sensors. So this is fiber optic construction. It is a core thin glass sector of fiber where light travels. So here it is a optical type fiber. So it is a fiber core. So within it is a glass type material where the light travels, and the cladding outer optical material. Cladding is outer optical material. This is fiber cladding surrounding the core. Buffer coating, it is a plastic coating that protects the fiber. So buffer coating is the plastic coating that protects the fiber. So this is a core buffer coating and cladding. So this is the arrangement of the fiber and its components. So principle of operation, fiber optic transmission of light depends on preventing light from escaping from the fiber, and here the light depends on preventing the light from escaping from the fiber. So it travels through fiber. It is an optical material. When a beam of light encounters a boundary between two transparent substances, some of the light is normally reflected while the rest passes into the new substance. A principle called total internal reflection allows optical fibers to retain the light they carry. When light passes from a dense substance into a less dense substance, there is an angle called the critical angle. So beyond which 100% of the light is reflected from the surface between substances. So that is 100% is transmitted. So that's why we have very negligible losses here in this optical fibers. So total internal reflection at some angle known as the critical angle theta c, light traveling from higher refractive index medium to a lower refractive index medium will be refracted at 90 degrees, that is refracted along the interface. If the light hits the interface at any angle larger than this critical angle, it will not pass through to the second medium at all. So instead, all of it will be reflected back into the first medium, a process known as total internal reflection. So that is if the critical angle, if it will not pass through to the second medium. So if the interface at any angle larger than its critical angle at this point of juncture, the total internal reflection takes place. So types of optical fibers. So here single mode fiber, multi-mode optical fiber. So multi-mode step index fibers, multi-mode graded index fibers. So first one is single mode optical fiber. This mode of optical fiber are used to transmit one signal per fiber used in telephone and optical, that is cable TVs. They have small cores, 9 microns in diameter, and transmit infrared light from laser. So multi-mode step index fiber. So here the index of refraction is a constant value. The core is made from pure glass, have a constant index of refraction, that is N1. The cladding also have a constant index of refraction, that is N2. So N1 is greater than N2. So here N1 and N2 are shown here. So this is N2 and this is N1. The first one is N1 and second one is N2, and here you can see the core. So this is N2 and this is N1. Core is having N1 index of refraction, and cladding is having N2 index of refraction. So multi-mode graded index fiber. So here the index of refraction change gradually at the area of core. So if it gradually changes from center of core, so n equal to n1 minus maximum value, and the separate line between the core and cladding, that is n equal to n equal to n2 minus minimum value, the gradually change take place take different shapes, that is triangular, parabolic. So these are the shapes. So here this is parabolic shapes taking place while transfer of data. So this is core and this is cladding, and this is N1 and this is N2. So here this type of fringes formed here. So multi-mode versus single mode. So here this is the cross section. This is multi-mode step index, single mode step index, multi-mode gradient index. So here this form this type of shapes taking place. It travels in straight. So here it travels in little zigzag ray propagation. So this is the simple differentiation between multi and single mode. So typical optical fiber sensing mechanism. So here this is the light source. This is a focal length. So transmission measurement. So here sensing element. So here these fringes are formed. This is photo detector, and reflection measurement. The light source, focus length, and the coupler, and the reflected back is measured or detected by photo detector. So this is reflection measurement. So light parameters, so here power intensity, the unit is watts, and attenuation, it is in terms of loss, that is decibels, and wavelength, spectral distribution, polarization, phase, optical path. So these are the parameters of light. So here optical transmitter. So it is a device that converts electrical signal into optical signal. So these are normally lasers. So Fabry to Perot lasers, FP lasers, distributed feedback lasers. So vertical cavity surface emitting lasers, that is VCSEL, ASC fiber laser, light emitting diodes, and surface emitting LEDs and edge emitting LEDs. So these are the two types of LEDs. And transmitter, the first one is FB laser. So radiation pattern is 60 degrees angle cone shape. So output power is several milliwatt, and modulation at high rates. Spectrum width is relatively big. And distributed feedback laser is single longitudinal mode, can be internally or externally modulated. So optical receiver definition, it converts optical signal into electrical signal. So that is optical receiver types. There are two types of optical receivers. One is PIN. This is nothing but PN type photo detector. It is a photodiode and a photon electron converter. Avalanche photo detector APD, more sensitive for high speed systems. APD is more sensitive for high speed systems. Photo detector parameters, responsivity, the amount of current produced per unit of input optical power. So that is responsivity. Wavelength bandwidth, the bandwidth, the PD is sensitive to photo detector is sensitive to. Damage threshold, the maximum optical power the photo detector can take before damage. So that is the threshold value. So this is the photo detector parameters. And this is the diagram of typical optical fiber measurement system. So this is the light source. It passes through the focus lens, and we have a sensing element, and fringes are formed between sensing element and lens. And lens is placed on either side of this sensing element, and finally we have photo detector. So this is the typical arrangement of optical fiber measurement system. So coupling light into fiber. So coupling light, that is sending the light into the fiber, that is coupling efficiency, numerical aperture of light source, dimension of light source, numerical aperture of fiber. Numerical aperture is nothing but the opening that receives the light, that is light. Fiber core diameter. So multi-mode fiber coupling, so this is another type. So there are two types, single mode and multi-mode. So in multi-mode it is widely used everywhere. So overfilled, and another one is underfilled. So in overfilled, high order mode in the light source will be lost into cladding area. So here this is happening. High order mode in the light source will be lost into cladding area, whereas underfilled is all mode available in the source can propagate along the fiber. So here underfilled is more losses are lesser, and this is preferred over overfilled. So this is how this is underfilled and this is overfilled. So cladding area, it loses to cladding area, the rays are losing to cladding area, so that is the drawback here. So coupling light into SM filter, that is single mode fiber. So this is the laser. This is with width of laser, and this is the diameter of the laser, and this is lens. This is focal length, and this is the width of the aperture, and this is the d diameter of the aperture, and this is the width of the rays. Here width of the rays, and this is the fiber including cladding. So this is how the arrangement is made, and through which the underfilled is preferred, and with that mode the for the light is sent into fiber. So this is a single mode fiber. So optical fiber sensor, a sensor that measures a physical quantity based on its modulation on the intensity, spectrum, phase, or polarization of light traveling through the optical fiber. So advantages of optical fiber sensors are compact in size, multifunctional, remote accessible, multiplexing, resistance to harsh environment, immunity to electromagnetic interferences. So these are all the advantages. And optical fiber sensor types, there are two major classification. One is intrinsic, and another one is extrinsic. The intrinsic is the effect of the measurement and the light being transmitted take place in the fiber. So that is the light, the measurement and the light being transmitted take place in the fiber itself. So the extrinsic is the fiber carries the light from the source and to the detector, but modulation occurs outside the fiber. So modulation is taking place outside the fiber. So that is why it is called as extrinsic fiber. So optical fiber sensor types. So one is a point sensor, multiplexed sensor, distributed sensor. So here the point sensor it detects the measurement variation only in the vicinity of the sensor. So within the vicinity of the sensor, it can detect the measurement. The multiplexed sensor, multiple localized sensors are placed at intervals along the fiber length. So multiple sensors are placed, localized sensors. So here in a point sensor you have within its vicinity, if it comes it can measure, otherwise it cannot detect it. Whereas in multiplexed, the localized sensors are placed along the fiber length. So distributed sensor, sensing is distributed along the length of the fiber. So sensing is done everywhere. So this is the point sensing, and this is multiplexed sensing, and this is the distributed sensing. So these are the three types of sensing techniques. So optical fiber sensor types here, intensity based. So again we can classify this. The intensity based, the measure physic measurement based on the intensity of the light detected through the fiber, that is fiber break. So interferometric phase modulation, So Fabry Perot, that is the FP interferometry, is a very popular one, and we have grating based wavelength modulation. So fiber branch grating, that is FBG, and long period fiber grating, that is LPFG. So these are the grating based wavelength modulation techniques. So intensity based optical fiber sensors having these advantages and disadvantages. So advantages: simple signal processing, inexpensive measurement instrument. Disadvantages are susceptible to power fluctuation of the light source, susceptible to the fiber bending losses. So variation in model power distributed in multi-mode fiber MMF. So that is multi-mode fiber. So optical fiber components, coming to components of optical fiber connector, broadband light source, that is BBS, fiber coupler, circulator, mode scrambler, index matching fluid, and wavelength division multiplexer. These are the major components of optical fiber system. So here you can see this is the body, the nulled nut. It is the nut for fixing the two components here, and we have retaining a ring and crimp frobble, and this is cable outlet jacket and bend relief boot, and we have ceramic ferrule. So this is a ceramic ferrule, and this is the coupler sleeve, alignment sleeve. So this is the fiber connector components and fiber connector structure. Fiber coupler, it is an optical device that combines or splits power from optical fibers. So it splits the power and from optical power. It is 1 by 2. From 1 it divides into 2. So there are many specifications available: 95 by 5, 90 by 10, 80 by 20, 50 by 50. So this is 2 by 2 coupler, and two receivers and two transmitters, and 1 into 2, 1 by 2, this is the coupler, and 1 is divided into 3 or 4 number of lines. So this is how fiber coupler works. So circulator, a passive three port device that couple light from port 1 to 2 and port 2 to 3 and have high isolation in other directions. So here from port 1 to 2 it sends, and also it from 2 to 3 it sends, and other everywhere it is completely isolated. So that is circulator. So this is the circulator is in a real it is seen like this. So mode scrambler, it is an optical device that mixes optical power in fiber to achieve equal power distribution in all modes. So this is the actual mode scrambler. This is the knob. So this is the knob, and with which you can adjust the power in all directions. So here mode stripper, an optical device that removes light in cladding of an optical fiber. So it removes light in the cladding. So cladding loss is reduced by this stripper. So index matching fluid. So here a liquid that refractive index similar to glass that is used to match the materials at the end of two fibers to reduce loss and back reflection. So it is a refractive index is same as glass fiber glass, uh, and because of this similar refractive index, there will not be loss in the light. And applications: reduce back reflection, increase coupling between two fibers. So that is the applications. Advantages of fiber sensors: many sensing applications could use mechanical or electronic sensors, but fiber sensors have advantages for some applications. So explosive environments, no electricity to start fibers, pressure sensors in rocket fuel tanks, so no electricity to start fires. So that is fires. And corrosive environments, silica fiber is chemically resistant unlike copper. Hot environments, many of these sensors work about 750 Fahrenheit and 400 degrees Celsius. The sensor can be cast into aluminum metal. So remote sensing, a signal detection processing can be done miles from active part of fiber sensor. So small size 125 micrometer fiber, same thickness as 36 AWG wire. So even uh, with the small fiber, we can transmit the light very effectively. So industrial use in oil wells, you can see this is oil well in some river bed. So oil well temperature monitoring measures temperature at 1 meter intervals along 10-kilometer deep well pipes with zero point 0.1 degree Celsius accuracy. So with just a single fiber, so it is with single fiber, the temperature is measured along the 1 meter, 10 kilometers deep well pipes also. Fiber optic gyroscope uses phase difference between two beams circling a fiber loop in opposite directions to very precisely measure rotation rate. So this is for gyroscope and fiber optic gyroscope. This is the phase difference between two beams cycling a fiber loop in opposite directions to very precisely measure rotation rate. So rotation rate is measured accurately. Precision better than zero point 0.1 degree per hour, readily done, can measure X rotation rate. Fiber gyros can be made extremely durable. They withstand being fired in the mortar shells also. So that much effectively we can employ the fiber optic sensors. So coming to the end of this topic, there are several characteristics of optical fibers that allow them to be used for sensors. These include microbending, interferometric effects, refractive index change, polarization change, fiber length change, fiber diffraction grating effects, and the Sagnac effect, light traveling in opposite directions around a loop used to sense rotation. So that is a Sagnac effect. So there ends this topic, fiber optic sensors, and you can see these books. These are the books you can refer, and the e-resources, and there ends this topic. Thank you, students. We will meet again in another topic in next session. Thank you once again.